Welcome back to the deep dive. We are jumping straight into the engine room of AI research today, specifically the fierce competition to make smaller language models smarter.
Right, without just having to, continuously inflate their size.
Exactly. This isn't just about parameter counts anymore. It's about making high-level reasoning AI more efficient, faster, and crucially accessible to everyone, not just the giants running these trillion parameter models.
Hmm.
So our mission today is a deep dive into a brilliant new method. It's called Think It Hard, or TIH.
And it's a mechanism that fundamentally changes how and when an LLM decides to spend its computational effort during a really complex task.
Okay, so for a learner trying to keep up with this field, what's the core challenge that TIH is trying to solve?
It's really about this performance ceiling that smaller LLMs keep hitting. I mean, models like Qwen 3.7b, they're strong. But when you throw a complex problem at them, like multi-step math or some kind of intricate logic, they run into what the researchers call hard tokens.
In a hard token, what does that actually mean from the model's perspective? Is it just a complicated word?
Not necessarily, no. It's more like a critical logical step. It's a moment where predicting the next token requires, a really extensive check of its internal facts or relationships.
So it's an inference step.
Exactly. And the standard single forward pass, that one quick calculation the model usually does, it just isn't deep enough to solve that challenge accurately. The model basically runs out of steam right at the most important part.
And traditionally, the old idea was just run it again, right? You just force the model to take a second pass at every single token.
That's what the previous recurrent transformer methods did. They tried to use a fixed number of extra passes. They called it the always think approach, essentially forcing every single prediction to be double-checked no matter how easy it was.
But this is where we hit this massive, really counterintuitive problem that TALH was designed to fix. Why does simply adding more fixed compute fail? You'd think more processing equals better results.
You would. But the research points to something they call latent overthinking.
Latent overthinking.
Yeah. When you force the model to iterate on every single token, the easy ones, the hard ones, all of them, you actually start to disrupt the predictions that were already correct after the first pass.
So you're breaking things that were already fixed.
Precisely. Imagine the model correctly predicts the word "and," but then you force it to spend 2 more computational cycles reviewing that decision. Those extra cycles can introduce noise and sometimes revise that correct prediction into an error.
The model starts corrupting its own simple, correct answers.
Exactly. The data showed this so clearly. Forcing a model to always think twice actually led to an increase in overall errors compared to just doing one pass.
That's stunning.
Yeah.
You add more computation, and you get lower accuracy.
It proves the problem isn't just how much computation, but how wasteful it is. The path forward isn't brute force, it has to be selective precision.
So this frames the central question of the research then. If fixed depth breaks things, can you train an LLM to use those extra iterations only on the few hard tokens that really need them?
And to answer that, they first ran an oracle experiment. This is like the perfect theoretical scenario where they simulate a model that could perfectly identify the hard tokens and only iterate on those.
The perfect internal critic.
Exactly. And if the model had this oracle, the accuracy gains on the math benchmark were just colossal. We're talking a jump of 25 to 28% over the always think model.
25 to 28%. That is a monumental gain just for being smart about when to spend compute.
It is. And that huge gap between the failure of always think and the success of the oracle proves that selective thinking is, well, it's the whole ballgame for small model reasoning.
Okay, so let's unpack the engineering puzzle here. The theory works, but, theory often breaks in practice. What were the big hurdles they faced, turning this perfect oracle idea into a real trainable LLM architecture?
Well, the first major one was architectural. This idea of dynamic depth, it fundamentally breaks the standard attention mechanism.
How so?
Well, think about it. If one token spits out its answer at depth 1, but the very next token decides to think deeper, maybe to depth 3, how does that deeper token see what the first one did?
Right, because the standard model just looks backward in the sequence, and it assumes all the previous tokens are sort of done.
Precisely. So TAH introduced something called duo-causal attention to solve this. Standard attention just looks back in time. Duo-causal attention looks back in time and up and down through the different iteration depths.
So it's attending in 2 dimensions.
That's a great way to put it. It allows that cross-depth information flow, all while keeping the training process efficient.
Okay, that makes sense. It lets the model keep the full context.
Yeah.
Now, what about the second challenge? This gets to the heart of refinement. The sources say something like 85% of tokens are correct on the first try.
Right. So the first pass needs to be fast and general, but the deeper passes, anything greater than one, they need a totally different objective. They need to be about error correction.
A fast writer and a slow, careful editor.
Yes, and they decoupled these two roles using LoRa adapters. For anyone unfamiliar, LoRa is basically a tiny specialized layer you add on top of the main frozen LLM, and these little adapters are only applied in the deeper iterations.
Ah, so the main LLM backbone stays untouched. It can keep being great at its main job, fast, general predictions, while the specialized LoRa adapter handles the really tricky refinement part.
It's a clean separation of duties. It prevents the refinement training from messing with all the general knowledge stored in the main model.
And the final piece of the puzzle is the decision maker itself. The thing that actually asks, do I need to think deeper on this?
The neural decider.
Right.
It's a pretty lightweight MLP. After each iteration, the decider looks at the model's internal state, basically how confident it is, and it outputs a continuation probability.
A confidence score.
Yeah. If that confidence falls below threshold, they set it at 0.9. The token keeps iterating. If it's confident enough or it hits the max depth, it verbalizes the token. That's the mechanism that makes sure compute is only spent where it's needed.
The system sounds really elegant, but it also sounds fragile. If the decider's choice affects the backbone's output, and that output is used to train the decider, you could get a very unstable loop. How did they train it?
You're right, they couldn't train them both at the same time. They needed to stabilize the target first. So they used a very clever two-stage training scheme, and it was all guided by an external oracle iteration policy.
So they bring the oracle back, that perfect theoretical critic, to act as the teacher for the real model.
Exactly. The oracle gives them a fixed, reliable ground truth. It uses another frozen LLM to classify every single token in the training data as either easy or hard.
So for every token, the oracle says, stop at depth 1, or no, this one's hard, go to depth 3.
That's it. And that leads to stage 1, backbone supervision. They trained the main LLM and the LoRa adapters, but they only calculated the loss. They only demanded a correct answer at the specific depth the oracle prescribed.
So it teaches the model when to be confident. It conditions it to trust the first pass for easy stuff and save its refinement power for the hard stuff in the deeper levels.
And once that backbone is trained to trust the system, then you move to stage 2.
Which is training the actual decider, the traffic cop.
Correct. Stage 2 is decider imitation. They froze the now conditioned backbone and just trained that little neural decider to mimic what the oracle was telling it to do. This decoupling is what guarantees stability.
It's a fantastic training approach. Now let's talk about behavior, because this is what really brings the tech to life. When they looked at which tokens were actually triggering that second iteration, the results are fascinating.
Oh, absolutely. The tokens that most often triggered the think twice response were but, with an amazing 34.3% continuation rate.
34% for the word but.
And the second one was so, at around 17.7%.
Wow. So it's not some complex scientific term or a tricky number in a math problem. It's the simple little words that either flip the argument's direction or introduce a cause and effect relationship.
It confirms the model is intelligently spending compute at critical logical points. These are the moments where you have to synthesize two contrasting ideas with but, or trace a dependency with so. The selective thinking is focused exactly where it should be.
So let's quantify the results then. What was the final impact?
It's really clear. TED got average accuracy gains of about 4.0% for the smaller model and 5.0% for the 1.7B model over the standard single-pass versions. And this was across 5 really tough reasoning benchmarks like GSM-8K and Math 500.
And the efficiency story here is what makes this a real breakthrough, isn't it? This accuracy boost came while only applying that deeper thinking to, what was it?
Roughly 6% of all tokens on average.
6%, that's the magic number.
It is. TED gets these better results while using basically the same amount of computation, the same FLOPs as the weaker standard single-pass model. It averages just 1.06 iterations per token.
And the always think model.
Oh, that one demands a rigid 2.0 iterations per token. So it's using almost 3 to 4 times the computational power for worse accuracy.
So Todd H gives you more thinking power for the same energy cost.
Exactly. More precision, same budget.
Let's bring this to life with that geometry problem you mentioned from the source material, the AME 25 one. It's a really complex challenge.
It is, and the standard model failed. The fixed depth always think model also failed. It generated a very long, very complex, but ultimately wrong answer.
But the time model got it right. Why?
Because it used that latent iteration to refine its logic. The neural decider signaled, hold on, this step in the coordinate geometry is low confidence, and the model took the extra pass it needed. It self-corrected and ultimately got the right answer, area equals 588.
That real-world example just validates the whole thing.
Yeah.
And the ablation studies where they took parts away to see what would happen, they confirmed it too, right?
They did. If you removed the Leray adapters or you took out duocausal attention, performance consistently dropped. Every piece of this carefully engineered system was necessary.
So what does this all mean at the end of the day? TH feels like a real paradigm shift for these smaller LLMs. We've moved from fixed, brute force thinking to, what, dynamic selective refinement.
That's it. The model itself decides when to pause, check its work, and think a little harder. And that delivers way better reasoning with almost no extra computational cost.
So if you're a learner trying to stay on the cutting edge, this is how we're building smarter, more efficient AI without just making them bigger.
Exactly. The future isn't just about how big a model is. It's about optimizing when it chooses to think.
That dynamic allocation is the breakthrough. But here's the final provocative thought for you to chew on. As good as the trained neural decider was, we have to remember the ideal oracle policy, the one that perfectly knew which token was hard.
Right.
That oracle still delivered that massive 25 to 28% higher accuracy gain in the experiments.
That gap. It suggests that the biggest performance bottleneck now is squarely on improving the accuracy of that initial decision. We've optimized the thinking process, but the decider that kicks it off still isn't perfect.
So the challenge that remains is, what fundamental insights about language or logic or even the structure of human reasoning are LLMs still missing? What do we need to learn to build a neural decider that gets the real-world TAH performance closer to its theoretical perfect maximum?
That decision-making engine, that's the next frontier.